So looking at general linear transformations that are performed by matrix multiplication, we want to investigate uh, the general linear transformation from an n-dimensional vector space V to any m-dimensional vector space W. And we're going to be looking at it from the perspective of using a matrix transformation from Rn to Rm, that is from n space to m space. So suppose that V is an n-dimensional vector space and that W is an m-dimensional vector space, and that the transformation T takes us from a vector space V to vector space W, and that's going to be a linear transformation. Hence, it'll be from n space to m space. And we know that this result could be achieved by matrix multiplication, paying attention to compatibility. Now, let capital B be a basis for V, vector space V, and capital B prime is going to be a basis for vector space W. So for each vector x in vector space V, the coordinate vectors for x and for t of x, which we'll refer to as the transformation vector, right, the vector in the new space W, we're going to look at those coordinate vectors in the usual notation. We'll put the square brackets around the vector, and we'll use a little subscript to refer to the basis that's being used to express it. So this will be the coordinate vector for vector x relative to basis b, and this will be the coordinate vector of the transform vector t of x relative to the basis b prime. So to accomplish this transformation, we really need an m by n matrix A that has the property that it takes us from the given vector x to the transformed vector t of x. So A would have to be, of course, compatible with this vector, this coordinate vector, x relative to basis b, and then we're going to investigate what are the properties with regard to the transform vector t of x relative to the basis b prime. So let's look at a specific example and get some ideas from the standard basis vectors for R2 and R3, which we're accustomed to denoting either as I and j, or E sub 1, E sub 2 for R2, and ijk, or E sub 1, E sub 2, E sub 3 for R3. So let T be a transformation from 2 space to 3 space. It's a linear transformation, and we are given the formula that performs that transformation for us. So if you take a vector in 2 space, a vector in R2, written in a column vector format, x1, x2, and you perform these operations on x1, x2, and takes you to 3 space, takes you to a vector in R3. Now if you look at this formula, this column vector in R3, you can easily see right through it and realize, well, that could be represented as a matrix multiplication. That is, we have this matrix, a 3 by 2 matrix, multiplied by this 2 by 1 matrix, x1, x2, the given vector in R2, and that would result in a 3 by 1 matrix representing all the vectors in R3 that we're looking for. So let's describe the results of the standard basis vectors of R2 under this transformation T. Again, the standard basis vectors for R2 is simply E1 and E2. Well, what does this transformation do to those vectors? Well, if you take a look, not surprisingly, when you transform 1, 0, that just captures the first column of your transformation matrix. So that would just give us the first column of the transformation matrix, 0, -5, -7. And if you perform this transformation on E sub 2, what we commonly call J, it just captures the second column of this transformation matrix. So we have 1, 13, 16. So it's very easy to see that this matrix in front of x1 and x2, it's called a standard matrix because a standard matrix simply refers to operations performed on the standard basis vectors of a particular space. So the results of multiplying by E1 and E2 are the column vectors of the standard matrix for T, the matrix that actually performs the transformation. And again, please recall that a standard matrix, the definition, a standard matrix has columns that are images of the vectors of the standard basis. So it's easy to see that when you're dealing with the standard basis vectors from one space to another, that a transformation on those standard basis vectors simply creates the column vectors of the transformation matrix that we need. So let's take a look at another vector in 2 space. Let's transform and see what result we get. Let's find the image of the vector 13, 5, and that's relative to the standard basis vectors E1 and E2. So that's what we usually mean by when we say 13, 5 as a coordinate. 13i plus 5j, another way of saying it. So let's find the image of that coordinate vector relative to the standard basis, E1, E2. Well, it simply means you substitute these values, 13 for x1 and 5 for x2. Or if you put them here, a nice way to look at it, column vector style for multiplication, 13 times the first column of the transformation matrix plus 5 times the second column of the transformation matrix. Adding that all up together gives us a vector in R3, in 3 space. We'll call it relative to the standard basis S prime. Here, S prime will be referring to E1, E2, E3 are what most people call I, J, and K vectors. So again, we have a transformation matrix A performing its transformation on a vector X relative to a basis B. In our case, the original basis B was the standard basis B, E1, E2, or I and J. And then it out pops a transformation vector relative to basis B prime. And basis B prime, in this case, we're going to call the standard basis vectors E1, E2, E3. And so here we have a coordinate, basically, or a vector in R3, in 3 space, 5, 0, negative 11. But now we want to generalize. What if we go beyond? What if we look at other basis vectors for one particular space to another? So let's take a look at the general theory first and see how it pans out with another example. So to generalize our use of an m by n matrix A with this property that matrix A times a given vector relative to basis B out pops a coordinate vector t of x relative to B prime, let's let B be a basis for an n-dimensional space. So here you have basis B, you have the basis vectors u1, u2, all the way to un because we're in n-dimensional space. And we'll have basis B prime in M space, so there's V1, V2, all the way to V sub M of them, since we're in an M-dimensional space, W. And since our transformation equation must hold for all the vectors in vector space V, we do know that it has to hold for the basis vectors, right? The vectors that actually form a basis for each vector space. So we could say that A times the first basis vector, u sub 1 relative to basis B, the first vector in this set, would equal the coordinate vector t of u sub 1 relative to B prime, the second basis here for W. And on you would go. So A times the second basis vector relative to B would equal the coordinate vector for t, the transformation of that second basis vector u relative to B prime. On it would go until you get to the last possibility. A times the last vector u sub n in basis B would be equal to the coordinate vector of t u sub n relative to B prime. But here's the interesting question. What would the coordinate vectors be for the basis vectors u sub 1 relative to B, u sub 2 relative to B, u sub n relative to B? What would the coordinate vectors be for each of those? Well, again, these are the basis vectors. So when you say, well, I want just the first basis vector, that's like saying, well, I just want the I vector from our standard basis. You would just write that as in 2 space, 1, 0, to indicate that you're having that first basis vector. And then you'd put the 1 in the second position when you were looking at the second basis vector, j, or e sub 2. And similarly, you go on down the line. Well, it works the same way for any type of basis. If you're referring to the first basis vector, its coordinate would be simply 1 in the first position. If you're looking at the second basis vector relative to the given basis B, that means a 1 in the second position, so on and so forth, until you get 1 in the n position. Now keep in mind, these vectors, u sub 1, u sub 2, all the way to u sub m, they're not necessarily the same as the standard basis vectors E1, E2, all the way to En. We're not saying that it's equal to, but we're just saying that the column vectors here that you see, the column vectors are simply the coordinate vectors relative to the given basis for any basis. If you're saying, well, what's the coordinate? How do you express the first basis vector as a coordinate? Well, you put 1 in the first position. How do you express the second basis vector as a coordinate? Well, you put a 1 in the second position, so on and so forth, and of course you put zeros everywhere else. That's a commonality with regard to any basis that you're using. The reason why that's useful to realize that is because it'll unlock an interesting little mystery with regard to how to get that transformation matrix A. So if you look back, we're trying to put these into the equations that we are using to represent the transformation. Here are the vectors for the vector coordinate vectors for each of the basis vectors relative to B. If you multiply it out, notice what happens once again. Transformation matrix A times the first vector u sub 1, the first coordinate vector u sub 1 relative to B, well, that would just mean we're going to capture the first column, right? 1 times the first column and 0 times all the other columns, well, that gives us just the first column. Similarly, A times the second coordinate vector of u2 relative to basis B, well, that has a 1 in the second position, so that just captures column 2. So on and so forth, as we go down the line, the transformation vector, the transformation matrix A times the coordinate vector for u sub n relative to B, well, that would just capture the nth column. Okay? So we're capturing one column at a time by multiplying by these particular basis vectors relative to basis B. What does that tell us? Well, again, if you substitute these results in the equations that we were investigating, all these transformations one at a time, you'll notice that that first column represents the transformation of the coordinate vector for transformation u sub 1 relative to B prime. And the second column represents the coordinate vector for the transformation of vector u2 relative to B prime, so on and so forth. The last column represents the coordinate vector for the transformation of u sub n relative to B prime. So this really shows that the successive columns of A are the coordinate vectors of all the transformations from u1, u2 to un with respect to the basis B prime. So if you put them together, they make what's called the transition matrix, if you will, or the transformation matrix T that we've been seeking to go from one space to another. So this a little notation here. You put square brackets around T for the transformation sub B prime comma B. It's read the matrix for T relative to the bases B and B prime. Basically what it means, no pun intended, basically what it means is we're going from basis B to basis B prime, and we're going to express the transformation results in that fashion. So the mystery that has been solved here is that the transformation matrix A, or what we're now going to call the matrix for T relative to the bases B and B prime, is simply taking all those coordinate vectors for the transformations of all the basis vectors in B and expressing them relative to the basis for the new vector space, which we call B prime. And you just augment, you perform, or you create an augmented matrix. You put all those columns that we had next to one another, and we get our transformation matrix. Much like we did before with the standard basis vectors, we realize, oh, you just put those next to one another, and that creates the standard matrix transformation. Well, now we're dealing with non-standard scenarios. We're going to generalize. And I find the best way to get your mind around this is to, again take a concrete example. So this matrix has the property that instead of having A here anymore, we're going to have this transformation matrix T relative to the bases B and B prime operating on a vector X expressed relative to basis B, and that's going to give us coordinate vector for the transformation of X relative to B prime. So in the notation, the right subscript that you see here is a basis for the domain T, and the left subscript is a basis for the image space of T. And a lot of authors talk about these two matching subscripts. It seems that the matrix equation subscripts here, the B's, kind of cancel out, and you're just left with the B prime. Okay, let's go back to that example we had before. We were going from 2-space to 3-space, a linear transformation defined by this expression here, this formula. Let's now describe the results and take it a step further. Okay. Well, we already know when we operate on the standard basis vectors, we get these column vectors which match the transformation, the columns of the transformation matrix that we could just see right away was producing the same transformation. And we said that the results are the column vectors of the standard matrix for T. And we also mentioned that the standard matrix has columns that are images of the vectors of the standard basis. Once again, we went back and we looked at transforming 13.5, and we transformed 13.5 into a vector in R3, and we got 5, 0, negative 11. Again, this was all done relative to the standard bases that we're accustomed to, E1, E2, or I and J, and E1, E2, E3, or I, J, and K. But now the question comes up, can we do this type of transformation, getting the same results, but just expressing ourselves in terms of other bases? And the answer is yes. Right? Is it possible to perform the same transformation on this vector in R2 with respect to a non-standard set of basis vectors? So let's take an example. First of all, how can we express this coordinate vector 13.5 relative to the standard basis, right? 13.5 means 13i, 5j, or 13e1, 5e2. But how can we express that relative to a different set of basis vectors? Here are two basis vectors, 3,1 and 5,2. I know they're basis vectors because they have to span R2 because they are two linearly independent vectors from 2 space. They're not multiples of one another. So they must be able to span R2. But how can I make the coordinate we're so familiar with, 13.5, by a linear combination of U1 and U2? Well, you could use your basic linear algebra to solve for that. Basically, what we're asking is, well, how much of 3,1 plus how much of 5,2 would give me 13.5? Obviously, this turns into a matrix vector equation, which you can solve in various ways. You might put it in an augmented matrix and take the reduced row echelon form. Or, since you know that the column vectors of the coefficient matrix here must be linearly independent, you can simply pre-multiply both sides by the inverse, which you know must exist, and out pops a new vector, a new coordinate vector, 1, 2, but this time it's relative to basis B. Basis B was the set of these two vectors, U1 and U2. So what this coordinate 1, 2 means, it doesn't mean 1i plus 2j anymore. It means 1 of U1, one of these vectors, 3, 1, plus 2 of 5, 2, two of the vectors U sub 2. Because there's a solutions to this system that we had right here. That's how many, or those are the multiples, that's the combination that we need of these two new basis vectors in basis B to get us the old standard coordinate that we're accustomed to, 13.5. Okay, so keep that in mind. So what we've done so far is we've showed how to get a coordinate for the basis, for the vector that we had before, 13.5, in terms of a new set of basis vectors. But now here's an interesting thought. These two basis vectors, U1 and U2, they're still expressed in standard notation, standard form, a vector we're accustomed to, 3i plus 1j, 5i plus 2j. We can actually perform the transformation on those using the standard transformation matrix. So if you do that, if you put 3, 1 into this structure up here, you'll get 1, negative 2, 5. If you put U2 into this structure, you'll get 2, 1, negative 3. If we let the basis for R3 now continue to be the standard basis, that is IJK or E1, E2, E3, then the matrix for T relative to bases B and B prime would simply be augmenting or putting together these two vectors to make a transformation matrix. Let's see how that looks. Let's test it out. Is it really so? Let's take this first column, 1, negative 2, 5. We'll put it in our first column of the transformation matrix. Let's take this second column vector, second to be 2, 1, 3. Let's put that as the second column of our transformation matrix from B to B prime. Let's take our coordinate 1, 2 relative to basis B. And what happens? 1 times the first column plus 2 times the second column. Let's check it out. 1 times 1 is 2. 2 times 2 is 4. 1 plus 4 is 5. 1 times negative 2 is negative 2. 2 times 1 is 2. Negative 2 plus 2 is 0. 1 times negative 5 is negative 5. 2 times negative 3 is negative 6. Negative 5 and negative 6 is negative 11. We get the same coordinate that we got in 3 space because we allowed B prime to still be the standard basis vectors for R3. So it works out. Of course, the next question would be, well, what happens if we then change the basis vectors for R3 as well? That is, the basis vectors in the vector space we're mapping to. Okay? Could we still affect the same transformation? That's a pivotal question. What if we use a different basis for R3 as well as for R2? Could we still affect the same transformation? Well, the answer is yes. Let's take a look. We have a little bit of work to do, but not much. So again, what if in addition to using basis vectors B, which is U1, U2, which we have over here, same ones, 3, 1 and 5, 2, what if we also use a new set of basis vectors B prime for R3? And here they are. I'm going to let the basis vectors in B prime be V1, V2, V3. Here are 3 linearly independent vectors from 3 space, so I know that they must span R3. They're a basis. Well, we still have that same formula, right? The question is, how can we express the transformation for U1 and U2 under this transformation matrix that we had? How can we express those two transformations as coordinate vectors relative to basis B prime? We already know the transformation of U1 under this structure is 1, negative 2, 5. We already know the transformation of U2, which is this vector 5, 2 under this structure, is 2, 1, 3. But we can't leave it at that because now these are expressions in terms of the standard basis for R3. How can we express these transformation vectors as coordinates relative to this new basis for R3? And much the same as we did before with a two-space problem, we can set up some systems of equations. And the answer, of course, is all predicated on expressing these transformation vectors as linear combinations of the new basis vectors instead of just leaving them as is in the standard basis for R3. So again, let's see what that looks like. Well, we would take our standard basis vectors, not our standard, but our non-standard basis vectors that we had from the previous slide, and we're asking, well, how many of them, right, multiplied together, how many of them under linear combination would give us this transform vector 1, negative 2, 5? And let's use a different method of attack. Let's do reduced row echelon form. We'll get 1, 0, 2. That means we have a new coordinate vector relative to B prime. Let's do for the other one. We had 2, 1, negative 3. Let's now use our new basis vectors and see how many of each would be needed. We get new coordinate 3, 1, negative 1. So how can we use these now to create the transformation we're looking for relative to these new vectors? So let's summarize what we've got so far. The coordinate vectors for these transformations, TU1 and TU2, are 1, 0, 2 and 3, 1, negative 1. So we simply take those two together. Now they're relative to B prime. We figured out these are coordinates relative to B prime. How many of those non-standard coordinate vectors do we need of each? What's the combination? Here's the first combination. Here's the second. Augment them together. Here's your new transformation matrix that'll take you from basis B to basis B prime. And what happens when we actually use that transformation matrix on our coordinate relative to basis B, which we're still going to use 1, 2? Well, it means 1 of the first column and 2 times the second column add together. So 1 times 1 is 1, 2 times 3 is 6, 1 and 6 is 7, getting different numbers. 1 times 0 is 0, 2 times 1 is 2, 0 plus 2 is 2. 1 times negative 2 is negative 2, 2 times negative 1 is negative 2, negative 2 plus negative 2 is negative 4. This doesn't look familiar. And it's not supposed to look exactly the same, but in a moment you'll see how familiar it really is. This simply means we're taking transformation from B to B prime on a vector x relative to basis B, and this new coordinate vector of the transform vector x relative to B prime is what this means. So this doesn't mean 7i plus 2j minus 4k, or 71 plus 2e2 minus 4e3 anymore. It means 7 of the first basis vector in the non-standard basis I gave, B prime, which was, I guess we'll call it just 7 times V1, plus 2 times V2 minus 4 times V3. That's what this means. But interestingly, if we actually worked it out, we should land at the same place in 3 space. It's the same transformation, just a different way of expressing it. Let's see if that works out. right? Is this the same vector in R3 that we obtained before? What was it? 5, 0, negative 11, something like that? Let's see. Is it really so that 7 times V1 plus 2 times V2 minus 4 times V3 gives us the familiar answer we had before? Well, lo and behold, 7 times 1, 0, negative 1. Let's see, 7 times 1 is 7, plus 2 times negative 1. 2 times negative 1, let's see, 7 minus 2 is 5. Negative 4 times 0, there's our 5. We get 7 times 0 is 0. 2 times 2 is 4. Negative 4 times 1 is negative 4. 4 and negative 4, there's our 0. And negative 7 plus 4 minus 8, there's our negative 11. So it's the same transformation. We're not doing something different. We're just going about it in a different way. We're expressing ourselves through the lens of a different basis for each space, from the domain to the codomain. So remember, a fixed linear transformation can have multiple representations depending on the bases chosen. We don't have to be held to just using the standard basis vectors in our transformation. We can use any basis vectors that'll do the job. So keep that in mind as you look for ways to express transformations using different types of basis vectors. And we hope you enjoyed this video.